Yes, I've sort of sneaked into this cutting edge session actually from inside Matterhorn Studio. And my role has been going on for maybe, I want to say a good maybe 6 to 9 months. I haven't counted it exactly. But I'm doing part-time work sort of on machine learning engineering and consulting for some of the open source Bayesian optimization platforms we've actually seen already. In my main job, I'm actually a PhD student, so I thought sort of with my maybe more junior experience, I could talk about my impressions of Bayesian optimization and experimental design in industry versus in academia, and then go on to talk a little bit about the exciting work we've been doing. So, um, I'm sure you're all quite familiar with Matterhorn Studios, right? So they're run by Jacob, and they've organized this active learning symposium, um, funded these incredible active learning grants, and I do really stress that you guys should find the video from the student that we unfortunately couldn't play on YouTube. They run a Bayesian optimization for Google Sheets. So this is supposed to make Bayesian optimization accessible to scientists who haven't got programming experience, for instance, which I think is really exciting. And then on my side of the sort of operations, we're working on with open source Bayesian optimization packages to provide extensions to the Bayesian optimization framework that they've already implemented. So we're talking about things like transfer learning Bayesian optimization, multi-fidelity Bayesian optimization, which I realized there was a question on in the question session. So yeah, I'll go through a bit of what these methods are, and some exciting sort of proof of concept for the programs we've made. So who am I working with? Well, yeah, so I sort of switched my camera off when somebody asked a question about the best open source platform, but I think all of the answers were spot on, right? Depends what you want, and they're evolving so quickly, and it's so exciting. So I'll be talking about projects I've done with the Process Optimizer, which is run by Novo Nordisk research, and I think has something to do with Brownie Bee. There's some integration going on, but I don't want to make claims about things I don't really know. So Process Optimizer, and then with Merck's Bayesian backend, and the work with Process Optimizer is completed work, and with Bayesian backend is sort of ongoing and very exciting too. So, just a couple of impressions, I thought. So I work partly with sort of wet lab biologists, and my impressions are that one factor at a time really is king. So in presenting to these sort of fellow students to try to convince them of Bayesian optimization as an approach, I showed them this sort of sketch here, right? If you start somewhere, optimize one factor, and then optimize the remaining factors, you'll end up deciding the best choice was over here. But if you just switch the order in which you chose to optimize the factors, then yeah, you could end up in a much better or a much worse place. And this is quite an arbitrary decision, right? When one designs a one factor at a time optimization, they don't necessarily think about what order of factors they're going to optimize. So I think I heard some gasps when I presented this sort of at school. So I thought I'd share it as well. Another impression from academia is that negative results or results that aren't too exciting, they go in the bin rather than in the compost being used for potential insights about future projects. And I wondered to what extent this is true or not in industry, and how methods such as transfer learning based on optimization could improve on this sort of practice. And then on the theoretical side, that there are plenty of really exciting methods, but they're often implemented in completely different ways on completely different platforms, sometimes in completely different programming languages. And in my impressions, for instance, BowTorch is obviously a huge library of plenty of Bayesian optimization methods. But actually, to be honest, is a little it hasn't got enough multi-fidelity. So we'll see a bit of that. Integrating all of these methods in usable packages could help really improve on these practices in academia, at least. And then from going from a student to somebody who's really considering problems that'll be used in industry. I've realized some of the key challenges are having customizability, mostly for the developers. So in the future, they can add methods that are more pertinent to the kinds of experiments that actually go on in the companies. But also having well-motivated defaults that sort of make sense as the thing you would choose if you weren't an expert in Bayesian optimization, and that's been really sort of eye-opening for me. Having a suitability of these methods over a range of search spaces is something that we kind of ignore in theoretical academic work sometimes. And in our projects, we've really aimed in having our custom acquisition functions be agnostic to the kind of search spaces you're looking at. So discrete, continuous, constrained, low and high dimensional. And then finally, the sitting right at the back of a lot of these methods are Gaussian process regression tools like GPyTorch on Python and tools with a whole library of acquisition functions and surrogate models such as BowTorch. And a lot of methods in academia aren't readily integrated. So we've sort of been producing a lot that I suppose translating methods from maths to integrable code, which has been really exciting. Okay, just to start off then on one of the projects, so transfer learning Bayesian optimization, I was involved in implementing for Novo Nordisk's process optimizer. And if you haven't come across it before, I think this diagram maybe gets things sort of makes things clear. So your task is to optimize the thing you care about, right? So this could be let's go with an example of some clinical drug studies. I'm not sure this is how it happens in real life, but let's just go with that example. So you might be trying out different conditions. And learning from your data and adapting across the process as you usually do in Bayesian optimization. But you have this existing data set on some other task. So maybe it comes from a simulation that you think is fairly representative of the task you care about, but you want to integrate it as just existing data to speed up the optimization of the thing you care about. So you could imagine, for instance, uh, a problem where your training task is very almost the same as your test task. And you can learn that quite quickly because wherever you take measurements for your test task, they look quite similar, very consistent with your training task. And if they're very consistent, you can become confident that that training data sort of is informative of where you should search next, and thus speed up your decision making. So let's just see that in practice, right? So this is in the process optimizer walkthrough. You can find it on GitHub. We have two tasks. So one of them on the left is our training task and looks quite similar to our test task. So we can imagine the one on the left is maybe a simulated example. The one on the right is what we actually see in the lab. And these tasks are like clearly systematically quite different, right? So if we look at this top right optimum, it's nowhere near the sort of what looks like the corresponding optimum on the left graph. So essentially, in the method we implemented, you can see it work if you take a bunch of data for the first task, and fit a posterior. This posterior looks very similar to the top left graph here. And then you utilize that data in your decision-making procedure and fit a joint posterior. And I think here we're plotting just the part on the test task, but you fit a joint posterior between your two tasks. And that posterior looks a lot more like the test task than your posterior for the training task. Um, and just for some like hard proof, if increasing the amount of data you have for your training task from nothing, so this is just doing standard Bayesian optimization, not utilizing the previous data you have, to including a lot of data, vastly increases how quickly, how many experiments it takes to get to a yield very close to the optimum. So. I hope that made some amount of sense. I'm just going to quickly move on then to multi-fidelity Bayesian optimization, which is in some senses similar to transfer learning Bayesian optimization. So here, we want to have efficient optimization over our target task, which is maybe this top left class of experiments. But we have a class of experiments that are indicative of that top left, and we don't know exactly in what respect, a bit like the case of transfer learning Bayesian optimization. But we imagine it's much cheaper to query this indicative task than the real task that we're trying to optimize. So the name of the game here is how much data and in what order do we collect about the cheap and indicative task versus the very expensive task we're actually trying to optimize. And I think I'll just before this, I will say it's a bit beyond just considering the cost, right? Because if you were just considering the cost and you actually believed that the indicative task was pretty much the same as the task you're trying to optimize over. So maybe you're considering yield producing a chemical and it's like temperature, and for some reason it's very expensive to make this setting very hot. But you actually find out you don't need to make it very hot in the first place, and you just go with the cheaper choice in the end. That would be cost aware Bayesian optimization, and that's something that we'll be using to compare to multi-fidelity Bayesian optimization in the future. But in multi-fidelity Bayesian optimization, your goal really is just one of these tasks. It's not either or. Okay. I think I'll sort of hurry up a little bit. So yeah, we implemented a method that existed in the academic literature before it was only available on sort of MATLAB, and also wasn't very easy to integrate with blowtorch's gradient-based optimization. But we were able to do that. And we went with this method over existing examples on blowtorch because they allow for this continuous or discrete design choices, and it's more readily integrable with the customizability in Baby. Um, Preliminary results, our methods sort of approaches the optimum choice a bit faster than either single fidelity or a fidelity less aware sort of method, and sort of baseline multi-fidelity methods. So very exciting. I think I'll quickly finish off with an open question. Is there a way, this is a bit related to the gray box optimization, right? So if you said, if an expert said, no, there's no way you'd run the cheaper experiment at a high temperature because that would just fry all of the samples. So therefore, we just shouldn't even consider that. How do you take this structural knowledge an expert might have and easily transfer it into sort of a surrogate model or a constraint set between the tasks that they can enter themselves without having to have statistical or mathematical background. So thank you very much, Jacob. I think I'll stop there.
Amazing. Yeah, thanks so much. I mean, this is, of course, a pretty good review of what you've done with Matterhorn over the last couple of months. So, yeah, and the great thing is, of course, it's all public as well. So, if anyone's interested, just check out Jordan's GitHub and you'll see the cutting edge contribution he's making to the ecosystem there.